Okay, here we go. This is the first week's lesson, kind of like an icebreaker to get you started on the material. And, the content here might be a little bit on the easier side, but hopefully at least you get used to the format of the delivery for this course. So I will be covering the first 12 pages of Chapter 4, which is titled the Pythagorean Theorem and Applications. So let's take a look at the first slide here. So what is the Pythagorean theorem? Well, really it just comes down to a relationship between the sides of a right-angled triangle. Now, I like this formula, a squared plus b squared equals c squared, but in reality, I don't usually label the triangle with a, b, and c. The big thing you got to remember here really is that the largest side is the quantity that goes by itself in the equation. So don't worry too much about these letters here. Just worry about that the quantity, which is here called the hypotenuse, has to be by itself in the equation. So what I'll do with you is sample some questions, examples, and exercises throughout the notes. And as you see on the bottom of each of these slides, I'll give you a page reference. So what you can do is pause the video and take a look at the appropriate page, try the question on your own, and then we can talk about it, or at least you can ask me questions through the chat or by email. What I might do in a supplementary video is answer any questions if they tend to be in a certain pattern. Also, from your questions I can gauge how more aggressive or more relaxed to go with the delivery. So here's our first triangle. So it is a right triangle, and we're looking to solve for x. What I'd like you to try is think about what is the longest side on this triangle. So in this case, the longest side would be the 11 inches. So when you write the Pythagorean theorem, don't worry so much about writing a, b, and c. Just make sure that you put the 11 by itself, and everything else will fall into place. So there it is. Now that you have this equation, you can use your calculator or basic arithmetic to just work through the rest. So for example, 9 squared is 81, and then you have 11 squared. So let's go through this one slowly. As we do more and more of these questions, I will cut out some steps, but for this first one, let's take it all the way to the end, nice and slow. So you get x squared is 40. To get rid of the squared, you can take a square root. Normally when you take a square root, you should write plus or minus, but because we are dealing with lengths, especially in construction, we'll always have a positive answer. And I will write answers accurate according to whatever the prescribed precision or accuracy is in the question. So in this question, when you look at the notes, it says to 3 decimal places. And that's it. A few things that I'm always looking for is making sure that you present the answer to the correct precision or accuracy and with the appropriate units. So let's take a look at the next example. What I've done now is dipped into some of the exercises. So again, pause the video, flip over to page 5 of the notes, and take a look at these two questions. I actually removed one of the questions that was in the middle there. I think these two permutations are decent and sufficient. So in this case, really just ask yourself where the longest side is. And in this case, the longest side is the hypotenuse, whereas is the variable, I should say. But in this case, the variable is not there. It's actually one of the legs of the triangle. So let's solve for x and for z in each of these triangles. So in the first triangle, we can take here and put the x by itself, and that will equal 3 squared plus 4 squared. This is the very famous triangle where the numbers work out nicely. 3 squared plus 4 squared is 16. I should say 25. I was going to do it in 2 steps. And then we can take a square root there and get 5. So that's the very famous 3, 4, 5 triangle. You probably see it a lot, especially with slope diagrams. Now, there are many of these types of triangles where, right triangles, where the numbers work out very nicely and they are whole numbers like that. They're called Pythagorean triples, and there's a whole mathematics behind that. You can look about it if you're interested. For this triangle, the longest side is 8. So let's put the 8 by itself, and then the other two sides on the left-hand side here. So let's just go through that carefully. If you don't mind, I'm not going to talk too much when I'm doing the algebra, unless there's something critical that I have to say. So this answer, when rounded to 3 decimal places, is 7.416 meters. So there you have it. This lesson won't take too long. Hopefully in the time frame of the 2 hours that you're allotted to cover this lesson, it's not too much of a stressful situation. In this next example, we have two triangles with decimal values for side lengths. This triangle has the variable over here, a. However, the hypotenuse is over here. So when you write the equation down, you're going to have the variable plus the 7.85 leg squared equals 10.44 squared. You can move the 7.85 squared over to get the following equation. And there is a squared here still, but we can undo the squared by taking the inverse, or in other words the square root, and putting that there. This is something that you could type all together on your calculator, and I encourage you to do that. I have done this already to save a little bit of time, and I got an answer of 6.88 inches. For the second triangle, the variable b is also the hypotenuse, or the longest side. Notice that it's opposite the right angle, right there. So when we write the equation, b is already isolated. So it's a matter of just writing down 4.605 squared and 5.228 squared. I mentioned earlier that I don't like writing a squared equals b squared plus c squared, or whatever way you want to write it, because the variables a, b, and c are abstract in the sense b here is the longest side, but what if c was the longest side? It's just a mess, so don't even bother trying to label that. Stick to the triangle and the notation that you're given, and it's probably safer for you anyway. Just remember longest side by itself. I can get rid of the squared here by taking the square root of both sides. I've already calculated this square root, and the answer I got was 6.967, and that's in centimeters. You can always check your answers by applying the Pythagorean theorem for the left-hand side and the right-hand side. So that's pretty much it. Alright, here's a little bit more complicated question. We have exercise 4 on page 5. The question here is to find the area of this triangle. This is an equilateral triangle because all of the side lengths are equal. You could also calculate some angles, but we're not going to use angles in this chapter. So how do I use Pythagorean theorem for a question where the triangle is not a right angle triangle? Well, symmetry can be used here because we can divide the triangle like that, or in other words, we bisect the angle at the top here, and that represents a right angle triangle. Look at that. We need to find the height h, and once we have that height h, we can do something in terms of finding the area, because the area formula for a triangle is half base times height. So let's go for the height. So the first thing that you can do is just draw the triangle here on the side, and let's talk about some lengths here. That's h. What's the base of this triangle? Because of symmetry, it'll be half of 10, so 5. And that's in meters, but I will omit the units for now. This side length is still 10. So what we can do next is find the height using the Pythagorean theorem. What is the longest side on this triangle? Well, it's 10. So just make sure the 10 goes by itself. So we have h squared plus 5 squared is 10 squared. Now, you can isolate for h. So I'll do that in here. That's 10 squared minus 5 squared. Of course, you could actually make those whole numbers and expand or evaluate the squared. Also, this square here, I can make it a square root by taking the square root of both sides. So h is the square root of 100 minus 25, or 75, which is approximately 8.660. Now that you have the height of the triangle, you can find the area. So the area will be half base times height. The height is 8.660. And what is the base? Well, according to this diagram, I could use 10 as my base. So, I mean, this is actually a really neat mental math question. You see here we have half times 10 times 8.660. Try this out. Take 8.660 and divide it by 2, because those are all even numbers here. And you would get 4.330. Let me write that down, 4.330. But we got to multiply by 10. So let's move that decimal over one spot, and look at that. Didn't have to pick up my calculator, and I found the area. Probably saved myself a few seconds there. And most of all, it probably built up my confidence. Okay, here's our next question. It's on page 6 also. It's exercise 5. The objective here is to find the length x here, this distance. However, now we have a compound figure. By compound, we mean that the figure has more than one shape that is attached. So we have a right angle triangle here. I'm going to call that 1. And then we have a quarter of a circle. That's part 2. And then over here we have another right angle triangle. So somehow you need to work through the figure to get to x. So let's move on to a more clearer image. Nice big image to work with here. Well, not so big as the previous one, but at least a workspace I can have. I would like to divide and conquer this figure as following. First, I need to get the overall height of this triangle. Second, I need to get the radius of that circle. And third, I can work on this triangle down here. So that's what I was saying earlier. And let's go through that right now. So let's get the overall height here. We can give that a name. I'll just call it y. So is y the longest side on triangle number 1? Well, no. 8.746 is, because that is the hypotenuse. So we would have y squared plus 8.746 squared is 5.829 squared. I have that backwards. That's not cool. Let's fix that. So I'll use a similar strategy as before. I'll move over the 5.829. And I will take a square root. This is something that you can type all together on your calculator. I have already done that. And I got 6.520. These units are in inches, and it's nice to show the units as you go along for each part of the question. So just keep that in mind. Item number 2 here is to get the radius of this circle. So we can say that the radius is half the diameter. So that's the diameter, and those digits are all even, which is very nice. So you can just divide them all individually. 2.431 inches. Now that allows you to actually draw and calculate information on triangle number 3. So down here, this is 2.431. But this length over here is a bit more difficult. So I'm going to just remove this triangle here. This length here is going to be 6.520, which is what y is, minus 2.431, which is what the radius is. because this length here and that length there are the same. I'll tick that off right here. So when you do that, you get 4.089. Now we can go back and write the Pythagorean theorem and solve for x. Since x is the longest side on this triangle, we'll have x by itself. So x squared equals 2.431 plus 4.089 with the squareds. We can take the square root of both sides, and you can do that in 2 steps. I'm just doing it in 1 step so that I have a nice compact presentation for you. Ultimately, when you evaluate that, you'll get x is 4.757 inches. Okay, let's take a look at the 3-dimensional question now. Here we have a pyramid, and it is a symmetrical pyramid with a square base. And the objective is to find a couple of lengths. Now, the first length here is AF, which is along the sloping edge here. And it's along the face, I should say. The second length is this sloping edge, length AC. Now, that is a mess. Imagine you're trying to talk to somebody by text or, for example, by email, describing how to solve this question. This is for very important reasons why I like to do something called draw a net. So what I'm going to do is just look at this figure a little bit more carefully and draw a net, which is a flattened 2-dimensional diagram that represents the critical information of this 3-dimensional diagram. So let's drop a vertical line to the center of this symmetrically based pyramid, and I'm going to extend a couple of lines there, actually just one with a right angle. Let's call this here O. So if we draw that triangle, what is the name of that triangle? Well, how about AOF? And see, like if you're talking to somebody by text or phone or email, you can say quickly, oh yeah, AOF, just look for that. Further to that, we can actually draw another triangle. Now here it's kind of hard to draw in 3D, but you can see it kind of folding out. I think I just clicked the wrong button on my stylus. Just like that, and I can unfold it, kind of like a book, the page of a book, and you get something like this. And that point there is C. Let's affix some lengths to these triangles. The height of the pyramid is 10 meters. That's given in the question. Now this length here that I'm going to double tick off is a 4 because it's half of the base length, 8, and this is also a 4. And when you draw them here, they're just 4 and 4. Now with this flattened image, you can see that the net actually turns the 3-dimensional question into something you don't need to look anymore at. I'll just get rid of that though. So part 1 of the question is to find this length, and part 2 is to find that length. So let's get AF. Since AF is the longest side of that triangle, triangle number 1 if you like, you just write down the Pythagorean theorem with a plus sign. 10 squared plus 4 squared, and you can square root that. So AF is going to be the square root of 116, or that's 10.77 meters. This is a little bit off topic, but I am going to put some interesting videos about how to do square roots like this to very good accuracy in your head. But for now, let's just use the calculator. Item number 2, we want the length here AC. So AC is the longest side of triangle number 2, so we would have AC squared. You could put a little line above here indicating line segment length if you like. I'll do that for this example. AC squared will equal AF squared plus 4 squared. Now the cute thing here is that AF we actually know is 116 with the square root. AF squared will be just the 116. So we can put 116 there, and we can put 16 here to get AC squared. If you want to get rid of the squared, you can take a square root. So that's the square root of 132. The square root of 132 is 11.49. Yeah, I cheated on that one. But under less pressure, I could probably do it in my head. So let's just leave it at that. Let's take a look at one more example. This is page 9, exercise 13. And it's a interesting figure. We have what looks like some type of a wedge shape here, but really what it has is an arc of a circle, and that's the key to this question. That's part of a circle. It turns out that when you do have a part of a circle, you can look at the radii at the edges or the endpoints of the arc as being important lengths. So what I mean is that this length here and this length here that terminate the arc are radii, and they are critical to helping you answer this question. So what I'll do is, just on a cleaner surface, go through the process to get us to the solution for x. So here's the diagram again, and let's divide off the picture to the two radii. So those lengths there are both 6.5 centimeters. And, well, still not really seeing how this relates to the Pythagorean theorem. Take a moment and think about that. Pythagorean theorem means right-angled triangles. So where the heck is a right-angled triangle on this figure? Well, it turns out there's two of them. There's one up here. I'll do that in orange. And there's one down here. And that one there, we can give those names and call them something nice. Let's call this one here triangle number 1. And let's call this one triangle number 2. What's important here is that overall, if I just quickly highlight it, what shape is that? Well, if you guess rectangle, you're correct. Since it's a rectangle, what you can say is that the top edge from here to here, that length must equal this length. So at the top, though, we have a 4 and an unknown side. Let's give that a name. We're going to call that W. And down here, the bottom edge also would be X and a Y. So what we can do is, from triangles 1 and 2, solve for W and Y. Let's do that right here. I'll solve for W first. On triangle number 1, let's just highlight that briefly in yellow. What's the longest side on that triangle? And the longest side on that triangle is the radius, 6.5. So that would be W squared plus 6.5 squared, plus 2.7 squared. Is 6.5 squared. We can move over the 2.7 squared and take a square root of that. And that would give you W is, and I'm going to take a look there on the side, 5.913. And that's in centimeters. Similarly, we can go to triangle number 2 and we can solve for Y. So how tall is this triangle? Well, the leg of that triangle, the height I should say, is 5.5 because remember, the bounding figure is a rectangle. So for triangle number 2, we would have, let's highlight that in blue, we would have the following. The longest side is still 6.5, which is the radius of this sector of a circle. We would have Y squared plus 5.5 squared is 6.5 squared. Did you know that it's actually really easy to do these squares in your head? And I will actually put a video about that too on this channel, just for my for your entertainment, and also just to kind of show you the kind of tricks I like to do if we were in class together, in contrast to being online and somewhat detached. So if you evaluate all of this, you're going to get a value of 3.464 centimeters. Now that we have W and Y, we can complete the question by solving for X. So you can say here that X plus Y is W plus 4. Before I put any numbers in, I'm just going to move over the y so you can see it as an isolated variable. And let's substitute now 5.913. There's the 4 we had earlier, and take away the quantity y, which is 3.464. That leaves us with an answer of 6.449. And that's in centimeters. Now, if you'll forgive me, these are approximate answers, so I should be putting the approximate equal sign. The good news is that if you don't put the approximate equal sign when you're presenting your answers to me, I'd be a hypocrite for taking marks off, because I tend to do it on occasion, off and on, I forget. So, with that in mind, we're done the actual calculations and exercises for this lesson. Hopefully it wasn't too stressful, but the book says that you should go up to page 12. So what the heck is on the remaining pages? Well, on page 10, you can see the solutions to these exercises. They're not full solutions, they're just the numerical quantities, the values that you should achieve. And although this is not something I would necessarily give on an assignment, I do present 2 proofs of the Pythagorean theorem on pages 11 and 12. These proofs are very old, actually, and come from all over the world, and they are not the only 2 proofs. There are many proofs for the Pythagorean theorem. So that's it for our first week together. Thank you so much for your time, and I look forward to the next meeting. If you have questions, comment below in the video or send me an email. Thank you.